Okay, here's part 2 of the lectures on refraction. Okay, before we begin to take a look at some example problems here, one thing that I forgot to mention towards the end of the last lecture is the following. When it comes to actually drawing out the geometry of refraction, and ultimately we're going to be leading towards understanding, for example, how lenses form images, well, we greatly simplify the refraction diagram, just as I did when talking about the law of reflection a couple of lectures ago. So here's the diagram that I had up on the board at the end of the last video. We have here light refracting, say, from air to glass, and it slows down as it does. Okay, we greatly simplify this diagram. Here's how we do so. Okay, so let's set it right here as the boundary, once again, between air and glass on the board above. And then we have our incident light ray coming in like so. Okay, and then just as we did when talking about reflection, what we do here is we draw a normal line, a dotted line that is perpendicular to the boundary between the air and the glass. And then right here is an angle that is formed by the incident light ray with respect to the normal line. This right here is the angle of incidence once again, just like it is when talking about reflection. So up on the top board, here's the incident light ray, and then right here is the normal line, and then right here, like so, is the angle of incidence. It's the same thing as this. It could be shown through some geometry. Okay, and then we have the refracted light ray that then looks like this from the top board, like so. So this guy right here that I just drew is the same thing as this. Okay, and then right here, another angle is formed with respect to the normal line. This right here is the angle of refraction, theta sub r. Okay, up on the top board, right here is the normal line like so for the refracted light ray. So right here is the angle that I just described. Once again, through some geometry, you could show that this angle here is the same thing as the angle of refraction. So once again, we simplify this diagram considerably, and then therefore, we just draw refraction in the following way. Okay? Okay, let me go ahead and do some erasing here. While I'm doing so, go ahead and access the first of the lecture examples for today. Go ahead and write down that example. Okay, specifically, we're going to take a look at, first of all, the first 3 examples here. Okay, the first one is as follows. Show that a light ray refracting from a window pane is parallel to the incident light ray if the sides of the glass are parallel. The index of refraction of glass is 1.5. For simplicity, let the initial angle of incidence equal 30 degrees. Okay, so here's what's being described. Okay, right here is my window, like so. So this is air, where n is equal to 1. This is glass, n is 1.5. And this right here is air, once again. And then as it says, the sides of the pane here are parallel to each other. Okay, and then we have our incident light ray coming in like so. Okay, and then right here is the normal line at that location. Right here is the angle of incidence like so. The angle of incidence here is given to us as 30 degrees. Okay, now let's just go ahead and use Snell's law. I've boxed it here above to go ahead and find the refracted angle here. As we do, we're going to see one of the basic rules for drawing refraction. There are 2. I'll describe them as I go. Okay, so here's then how we apply Snell's law for this first refraction. This right here is n for air, which is 1, times the sine of 30 degrees for the angle of incidence. This equals then the index of refraction of glass, 1.5, and then multiplied by the sine of the refracted angle. And then in degree mode on our calculator, all that we do here is just solve for the refracted angle. So I'll go ahead and do so. So on the left-hand side, I just have the sine of 30, which is a half, divide by 1.5, and then take the inverse sine of that. And as I do, the angle of refraction is about 19.5 degrees. Okay, so then therefore, when light slows down as it passes from air to glass, the refracted angle is less than the incident angle. So then therefore, the refracted light ray looks like this. Right here is the angle of refraction. And this illustrates then one of the basic rules for refracting light rays and drawing them as you go. Okay, when light propagates from a low to a high index of refraction, The refracted angle is less than the incident angle, therefore you refract your light ray towards the dotted line. You refract towards the normal line. This is the first of these two rules. So when light refracts from low to high index, you refract towards the normal line. Or bend your light ray towards the normal line. That's the first of these two rules. Okay, the second rule, as we'll see that as we now propagate from high to low index refraction. That is, we go from the glass to the air. Okay, now right here is a new angle of incidence. If I describe it on my diagram like so, let's refer to this new angle of incidence here as theta incident prime. Okay, now theta incident prime very simply is the same thing as the refracted angle from earlier, because the sides of the glass here are parallel to each other, and then therefore these normal lines here, these dashed red lines, they are parallel to each other as well. So then therefore, pretty obviously, the angle of incidence here, theta incident prime, is just 19.5 degrees. Okay, now let me just write Snell's law again as the light propagates from the glass to the air. In this case, the left-hand side of the expression is going to refer to what is going on in the glass, and then the right-hand side refers to what happens as I refract into the air. So first of all, on the left-hand side for the glass, we have 1.5, and then multiply by the sine of this new incident angle of 19.5 degrees. This then equals n for air, which is 1, multiplied by the sine of the new refracted angle. I'm going to call it theta refracted prime. Notice that this expression here is just the same thing as this expression here, except the two sides of the equation are just backwards. So then therefore, if you run through the math here, pretty obviously the refracted angle here, theta refracted prime, would equal 30 degrees. Notice it's a bigger angle than the angle of incidence when we refract from high to low index of refraction. This is the second rule. I'll write that down for you in just a moment. But when you refract from high to low index of refraction, you refract away from the dotted line. That is like so. Right here is the refracted angle, theta refracted prime. Let me go ahead and write down that second rule. Okay, so when light refracts from high to low index, you refract away from the normal line. That's the second rule for drawing refractions quickly. And now let's just go ahead and answer the problem as it's stated. Notice that this refracted light ray here that emerges from the window pane is in fact parallel to the incident light ray here. That then answers the questions as it's stated. Here's, however, what you see when you actually look through a window pane. So let's say your eye, for example, is right here like so. And then you look at an object that is right here and a light ray is coming from that object. Are you looking at that object in its actual position, or does it appear to have an apparent position? It appears to have an apparent position, because when the light here enters your eye like so, notice the direction that you're looking. The direction that you're looking is like this. So this right here is the object's actual position. This right here, however, is where you appear to see the object. Its apparent position. There's a little shift here. This shift here between the object's actual position and its apparent position, however, is not that much. It depends upon exactly how thick the pane of glass is. So if you're talking about an ordinary window pane, which is usually very thin, then you're never really going to notice this shift between the object's actual and its apparent position. However, if you have a really thick piece of glass and you look through it on an angle as I'm describing here in this diagram, then you're going to see a noticeable shift in the object's apparent and actual position like so. Okay? All right, that's the first of these three examples that we're looking at here in this lecture. Go ahead now and access the second example. Okay, the second example involves a swimming pool. Those of you who have easy access to a swimming pool at home or at a friend's house, well, you'll actually be able to see this. I'll describe it for you as I complete the problem in just a few minutes. Okay, let's just look at the problem itself. So a vertical pole, it's 2 meters tall, it's standing upright in a pool. The pool of water itself is 1.5 meters deep. Okay, sunlight is incident upon the pole at a 45-degree angle. What is the length of the pole's shadow on the floor of the pool? N is equal to 1.33 for water. All right, so here's what's being described. Let me go ahead and draw the pool of water, like so. Okay, and then right here is the vertical pole, like so. And then we're given some distances here. Okay, first of all, the depth of the pool, I'm going to call that D. That's given to us as 1.5 meters. And then right here is the height of the pole. Let's just refer to that as H. That's given to us as 2 meters. Okay, and then we have sunlight that is incident upon the pole at a 45-degree angle, and that then causes the shadow to be cast onto the floor of the pool. So right here is the incoming light, we'll say, like so. Let me complete this diagram here a little bit better. Like so. Okay, and then right here, call it theta for now. This right here is the 45-degree angle that we're given, and this is the incoming light ray, like so. Okay, and then the light is incident upon this boundary here between the air and the water. The index of refraction of air is 1.1 rather, and the index of refraction of water is about 1.33. Okay, now right here at the boundary between the air and the water is our normal line, like so. So right here is the angle of incidence. Pretty obviously, the angle of incidence here is the same thing as the 45-degree angle that was given. Okay, and then we get to one of the rules, still on the right-hand board, for refracting this light ray. In this case, we're going from low to high index, so you bend towards the dotted line. That is like so. And then right here is a refracted angle, theta refractive. So let's just immediately use Snell's law here to calculate the refracted angle, and then after that is just some geometry here involving sides of triangles. Okay, before we get to that, though, let's go ahead and do the refraction here. So I have, first of all, N for air, which is 1, and then times the sine of 45 degrees. This equals N for water, 1.33, times the sine of the refracted angle, and then I just do the math here to find the refracted angle. It's going to be less than 45 degrees. Okay, so the left-hand side is the sine of 45, and then divide by 1.33, and then take the inverse sine of that. Okay, and then ultimately this angle here, theta refracted, I'll round it off a little bit, is about 32 degrees, like so. Okay, now what are we asked to find? We're asked to find this distance right here. This is the length of the shadow that's cast on the floor of the pool. Let's refer to this as L. In order to do so, let's go ahead and label some sides here of triangles. Okay, so let's call this distance right here, which is the same thing as this. Let's refer to this as A. Let's call this distance here B, like so. And then recall that this distance here is the same thing as the depth of the pool. We were calling that D earlier. So basically what I have to do here is a little bit of geometry and figure out what A plus B is. That's then going to be the length here of the shadow that's cast on the floor of the pool. Okay, so let's take a look at this right triangle right here, and we're going to do a little bit of tangent here in order to find out what B is equal to. So tangent of theta refracted is equal to opposite over adjacent, so B over D. Okay, cross multiply to solve for B, like so. All right, so let's see, the depth was 1.5, multiply that by the tangent of 32 degrees, and that comes out to be about 0.94 or so meters, like so. Okay, and then lastly, I have to find this distance here. Okay, right here is a little right triangle like so, This distance here, remember, is equal to 2 minus 1.5 meters. Let's give this a name here. Let's call this C. This is equal to a half a meter. Okay, this right here, by the way, is just an isosceles right triangle. So then therefore, if this is a half a meter, this is also equal to a half a meter. Like so. So then therefore, the answer is just A plus B for the length of the shadow. All right, so 0.94 meters for B plus a half a meter here, that's 1.44 meters like so. And this then just completes the problem. Okay, here's how you can see this. So for example, let's say that right here is a light emitting object. Let's say that there's something just on the floor of the pool. And then you're standing out here in the air and you look at that object on the floor of the pool. Does that object appear to be further from you than it actually is? Or does it appear to be closer than it actually is? Well, notice how the refraction here occurs. Light comes from the object, refracts then into the air, into your eye. So let's say your eye is over here. And then therefore, notice the direction that you're looking. You're looking in this direction like so. So the object appears to be further from you than it actually is. The next time you stand on the side of a pool, look down into the floor of the pool, pick a spot, and you'll see that it looks to be a little bit further away from you than it actually is. Okay, how big of a shift there is between the object's actual position and its apparent position depends upon the depth of the pool. Okay? Okay, now at this point, let's go ahead and take a look at the third problem, which has to do with prisms. After I conclude this problem, then what I'm going to have you do is take a look at a prism demonstration. But before you do that, let's look at the actual problem itself. Okay, so we have light incident upon a triangular prism. Okay, so here's my prism, like so. Okay, right here is what is referred to as the apex angle of the prism. It's usually referred to as phi. In this case, it's given to us as 60 degrees. Okay, and then we have air, glass, and then back to air once again. Okay, light is incident at a 30-degree angle upon the prism. That 30-degree angle specifically refers to the following. Okay, so we have light coming in, we'll say like so. Okay, and then right here is the normal line. Right here is the angle of incidence, the theta incident that's given to us as 30 degrees. Okay, and then let's just write up the refractions here. Let's go ahead and draw them out before we start to make some calculations. Okay, the light initially is going to refract from low to high index of refraction. So what I'm going to do is bend it towards the dotted line, like so. And then right here is the refracted angle, theta refracted. Okay, this light right here, by the way, is not necessarily parallel to the base of the prism, so just be careful of that here as we draw. Okay, and then right over here is another normal line like so, as now the light's going to refract from the glass to the air. So right here is a new angle of incidence. We'll call this theta incident prime, like so. And then we want to describe the refraction out the other side of the prism back into the air. Just in terms of drawing it, now in this case we're going from high to low index of refraction, so you bend away from the dotted line, like so. And then right here is the final refracted angle, call it theta refracted prime. That's ultimately what the question is asking us to solve for. Notice, by the way, that there is a big redirection of the direction of the light itself as it refracts through the prism. It initially is propagating this direction like so. When it eventually emerges out the other side of the prism, it's propagating in this direction like so. There is a big angular shift here like so when you take the two sides of the glass and then tilt them with respect to each other. For now, we're ignoring the colors that you would see when you look through a prism. That's specifically in my short video of the prism demonstration. We'll get to that, however, a little bit later on. Okay, now let me just go ahead and run through Snell's law here and then some geometry of the prism itself to ultimately find this refracted angle. So first of all, we apply Snell's law here at this interface between the air and the glass. So I have N for air, times the sine of the incident angle equals then n for glass multiplied by the sine of the refracted angle. The numbers that we see here in this equation, by the way, are actually the same from the window pane problem from a little while ago. If you run through the math here, the refracted angle is 19.5 degrees. Okay, here's then how we use that 19.5 degree angle to find this incident angle over here. And now this is where the geometry of the prism itself becomes important. Okay, let's define two more angles on this diagram. Let's call this angle here alpha, and this angle here beta. So take a look at alpha first. Notice that alpha is the complement of this refracted angle. So alpha is 90 minus theta refracted. So let me go ahead and find that. So 90 minus 19.5, that's 70.5. Like so. And now I have right here a triangle, and the sum of the angles in a triangle, remember, is 180 degrees. So alpha plus beta plus phi is equal to 180. Let's go ahead and use that then to find beta. So beta is going to be 180 minus alpha minus phi. So that's where the apex angle becomes important. So now I've got 180 minus 70.5 minus 60, and that comes out to be 49.5 degrees. Okay, now that I have that angle, now let's go ahead and find theta incident prime, because notice that theta incident prime is the complement of beta. So theta incident prime is 90 minus beta. So 90 minus 49.5, and that comes out to be 40.5 degrees. Okay, now that I've run through these geometrical steps, now I once again apply Snell's law as the light refracts here from the glass back to the air. So here's then what we get with Snell's law. Let me switch to a different color myself. Okay, so now I'm going to have n for glass, 1.5 times the sine of 40.5 degrees, this angle here. Okay, this then equals n for the air, which is 1, multiplied by the sine of the final refracted angle, theta refracted prime, and now we just go ahead and solve. Okay, so 1.5 times the sine of 40.5, and then inverse the sine of all of that. So after you do the math here, the refracted angle out the other side is quite large. It's 77 degrees. So you end up with this big redirection of the light as it refracts here from the air on this side through the glass and then out to the air on the other side. When you take the two sides of the glass here and you then have them offset from each other, they are no longer parallel to each other like we had in the window pane problem earlier. Okay, now when you normally look through a prism, and I usually do pass them around the room, in addition to seeing a big redirection in the direction of the propagation of the light, you also see the component colors, Roy G. Biv, of white light. Why is that? At this point, you can go ahead, by the way, and pause this video, and then take a look at my short demonstration video on prisms. Okay, in that demonstration video, you are seeing examples of what is called dispersion. Let me describe what that is. Okay, as I've described, when light interacts with matter, it slows down. But it doesn't slow down by the same amount for all colors or wavelengths of light. The wavelength itself is important. What this means is that the index of refraction of light for a material is actually a function of the wavelength of the light itself. So in actuality, the index of refraction is a function of the wavelength. So let's say that we're talking about glass, which, as I've indicated, has an index of refraction of 1.5. Well, it's not quite exactly the same number for all of the different colors of light. Blue light which has a shorter wavelength than red light, actually slows down a little bit more than red light does. This then ultimately means that the index of refraction for a material for blue light is a little bigger than it is for red light. It's not by all that much. Usually the difference between the indices of refraction of the two different colors goes out just several decimal spaces. However, they are slightly different values. So then therefore, let's say that we have light of two colors, say red and blue, striking the prism. The index of refraction for blue light is a little bit greater than it is for red light. This then allows us to begin to split the light or disperse it into its component colors. So let me go ahead and now redraw the diagram for the prism involving just two colors, red and blue. And as I do, you're going to see basically the artwork of a very famous album cover emerge. Hopefully everybody is familiar with that album cover. If you are not, then your education is sorely lacking. At any rate, however, here's dispersion through a prism. Okay, so here's my prism from earlier, like so. Once again, let me just go ahead and label the apex angle here phi like this. And now we have light of two different colors. So we've got blue light like so, and then red light like so. Okay, and then right here, once again, there's our dotted line that is perpendicular to the surface. So then therefore the light begins to split into its component colors because the index of refraction for blue light is a little bit more than it is for red light. So I'm now going to split the two colors up, and what I do, I'm going to bend the blue light towards the dotted line a little bit more than the red light. So that then looks like this. So here's the blue light refracting, like so. And then here's the red light refracting, like so. And I begin to split up the colors or disperse them, as we said. Okay, now at each location I'm going to have here, that is here and here, I'm going to have normal lines. So right here, there's a normal line for the blue light as it refracts then from the glass back to the air. Right here is a normal line for the red light as it refracts from the glass back into the air. Okay, now as I refract these two light rays, I'm going to be bending away from the dotted line. But when I do this for the blue light, I'm going to bend it a little bit more than I do for the red light, because once again, the index of refraction for the glass for the blue light is a little bit more than it is for the red light. So then therefore, the blue light I'll bend away like so. And then the red light, I'll bend away like so. And then if you did this for white light, which is a combination of the entire Roy G. Biv, then you can begin to split white light up into its spectrum. You would see the Roy G. Biv like so, resulting, for example, in that very famous album cover. Here's one of the applications of doing this, not necessarily with a prism, but just dispersing white light into its component colors. We could use this, for example, to study the light associated with the sun. When you have the sunlight coming in from the sun itself, well, that light is basically white light. It's composed of the entire Roy G. Biv. And then we can pass that light through a prism, for example, like so, to begin to split it up into its component colors and then study properties of the sun in that manner. Okay, let me go ahead and conclude this here as part 2 of today's lectures on refraction.